devices, and gaming definitely is an important thing that most people do on a lot of these devices. And so some trends that show that, over a period of time, the gaming devices have been growing. People have been looking at more than one device on which they game. And how many of you use more than one device at home to do some gaming? A lot of you, right? Me too. So I do phones, I have consoles, tablets, so we all do that. And the second part, obviously, is no surprise, right? So we want to have a cross-platform, but HTML5 is not quite there yet. So from a performance standpoint, it's the biggest gripe that every developer will have, that we can't do good enough cross-platform with this. And obviously, the bigger problem now is that we have a lot of new trends coming. So people, we have great announcements on virtual reality. I just saw in CES some announcement around smart glass and how you can augment your games, and cross-platform, and augmented reality-based games. So what does it all mean? The hardware is very capable, but if we want to do cross-platform, we really need to catch up on the software side and make it happen. Otherwise, a lot of this is going to be native, and we won't be able to take it forward on a cross-platform front. So that's the motivation for us to look at this, right? So, and we said, okay, our mission then in that case is, how can we enable this great desktop class gaming experience and bring it to all devices, and devices with varying capabilities? And so this is something that Samsung's ecosystem would look like. So you have all these categories of devices that exist in Samsung's ecosystem, and we want to enable on these devices really good quality gaming experience. And if you want to do that, I think it's going to be all these categories of games. So today, I think casual probably is the one that gets close enough attention on the HTML5 front. But there's mid-core gaming and really core gaming, which is non-console based. If you can enjoy not having to do native, then it's great. And so we have looked at 2D as well as 3D aspects of gaming and how performance in each of those vary. And obviously, the three important paradigms we look at is HTML5 and JavaScript engines, the heterogeneous computing, which I'll talk to you about in a little bit, and how we can actually bring these to game engines and how game engines can take advantage of it. So developers like you can actually build some great games using the hardware's power. Okay, so PC gaming, so I think this is no surprise to most people. So if I take a look at what a PC is and what a phone can do and what a wearable is or any of the smaller devices are, there's huge footprint variance across memory, right? You can go anywhere from 8 GB to 8 MB or less. And there's differences in cores that you have to consume, 1 to 16 or 32. And if you look at the JavaScript engine, how it's tuned in the performance, there is actually a lot of variation in that as well, as even if there's a web engine that runs on it. And if you look at the device itself, from a hardware standpoint, there's a lot of capabilities, and every year, people squeeze in more capabilities in the hardware, right? There is multi-core, which is MIMD capable. There's graphics with tons of cores. There's audio processing, image processing, so you name it. Everything has an engine and a pipeline that you can explore, and you can use it effectively for your gaming optimization. So from there, so if you look at the computing, what's happening, so I think how people have traditionally explored and exploited this at a higher level is it all started with OpenGL and DirectX way back in early 2000s. And the standard actually helped stream processing, right? So you were able to do a lot of the shaders and vertex programming, basically the streams of multiple data that you can bring to a graphics core, right? And this enabled you to do the graphics optimization alone. And you actually took it next step forward, and the CUDA came along and OpenCL, and obviously you were expanding the range of things that you want to be able to do, and so the GPU programming was born, so more general purpose computing, but something that is more constrained in the graphics realm, right? It's not very intensive, complex operations, but something that a graphics core can actually handle. And so this is where we think we are right now, which is where WebGL, I'm sure there's been a lot of discussions around that as well. And so we're introducing what we're talking about. We'll talk about WebCL, which is sort of the counterpart to WebGL, where we can do a lot of the cross-platform processing. So the concept, what we call as heterogeneous computing, comes into play. And I'll talk a little bit right now. So the idea is your core is very capable with all these different engines, and you want to be able to take at a very highly abstracted level, at a web level, advantage of everything and write a very simple kernel that can actually take advantage of this. And we think we're going to much more heterogeneous computing, which we'll call as heterogeneous cloud computing, where you will have more complex workloads in the future, and they're going to be divided more between the device and the cloud. And so obviously we need to enable this today so that we can enable that future soon, which is not far away. We already have a lot of cloud gaming, but the device itself needs to have the ability to split the load between the cloud and the device so that we can take advantage of it. So that's where I think we're calling it as the heterogeneous parallel computing era. So using all the hardware resources and really exploiting a lot of parallelism to take advantage of it and get the most performance is how we're going to get to that high quality cross-platform games we talked about. Okay, so what is heterogeneous parallel computing? Simple. The idea is all these things that are shown at the bottom, the hardware component, the processing power is there today in the hardware. CPU, GPU is very capable. But if I ask you the question, do you know how much of that capability you actually know how to use in your games? Or you actually understand that you're using it fully to develop the best quality games? And I suspect a lot of you can answer that directly, right? We all optimize and try to get the best performance for that given game, but we actually don't know how far we can go and how good a game we can actually develop on top of it. And that's mainly because the application and the frameworks are not mature enough to enable very granular access to these devices and really be able to measure those performance so that you can actually tune and say, hey, my graphics actually is this capable. Oh, okay, maybe I can actually do these other things on the graphics side, while the compute side can take care of these other issues. Well, we don't have all the answers right now. Especially in the web realm, it's far behind. And I think that's one of the key issues, and the idea of parallel computing across multiple cores is what the concept of heterogeneous computing is, and that's where we actually are today. So now, given that, I think, so this is just a quick intro slide saying that, we actually have a lot of parallelism. Believe it or not, everything that we do, if you want to find parallelism, there's a lot of areas where we can find parallelism. It's just that, for example, graphics has traditionally done that for rendering part of it, right? But if you look at all of the logic and the computation, there's significant amount of parallelism, and I'll show you in gaming where we can find parallelism. And people, it's usually a hard learning curve to understand how to use parallelism effectively. And also the fact that people don't know what is data parallel and instruction parallel, and they actually give up, not understanding that data parallelism is where you get the most benefits in parallelism. So some examples, right? So you look at 3D graphics, all those are examples of parallelism. Video is actually becoming much more richer formats, and of course, a lot of these can be, and the video engine is getting more powerful to render these things. And same thing with image processing. So when you look at, so WebCL. So what WebCL is in simple words, it's an engine. It's just a binding that we have developed for JavaScript that exploits OpenCL kernel. And you can develop on the web layer simple kernels which can exploit the raw parallelism that your device provides. And when I talked about 1 core to 32 cores, that's where this comes in, right? Knowing the capability of the device, you can easily write the kernel, and you can go between devices and tune it very easily. And that's the idea behind using WebCL for your development. So the goal is it gives you high performance, enables a lot of compute-intensive applications. It is platform independent, right? It's portable across multiple heterogeneous devices. And so obviously you can write a game for your desktop. And when we talked about our vision, it was, hey, can I have the desktop level gaming onto my other devices? Yes, you can. And this is a starting point where you can start exploring that concept. OK, and currently, just like WebGL was standardized, it's going through Chronos standardization process. So that's something that we have worked on. So the takeaway should be for high performance web computing, if you want to think of one word, think of WebCL and learn more about it and see how you can use it effectively. And why WebCL? I think there's a lot of use cases that we have looked at personally that WebCL helps with. 3D gaming obviously is a big one because a lot of data parallelism. And then big data, augmented reality, video processing, photography, we have use cases that we have looked at from all of these areas. Okay, and so this is a simple introduction on how it plays out in our operating system Tizen that we have developed. So Tizen has the native libraries in which OpenCL can be actually integrated. And we have done that for some OpenGL ES for Cairo, and we have done OpenCL integration into the core for native libraries. And on top of that, we have the web engine, right? And the web runtime actually integrates WebCL. And that's where you can access WebCL. And framework will sit on top of it, which can talk to WebCL and, in effect, talk to OpenCL and go down and access the hardware. And so those are some of the frameworks. You probably are familiar with a lot of these. And anybody can integrate those into the frameworks to make it happen. And the gaming applications on top. So if you wanted to know in gaming arena, where WebCL plays a big role, these are all the areas that we have actually personally looked at. So collision detection, so any 2D and 3D rigid body dynamics or soft body dynamics, it's all compute intensive and it's got a lot of parallelism already in it. So the best way you want to write this is using a WebCL kernel so that your device actually doesn't run too hot, gets power managed properly, and you actually use all the cores effectively. And soft body, fluid body, pathfinding, vision cones, dynamic simulation, any of these, and all the high-end gamings today, you would find any of these effects. And definitely WebCL is the best candidate that you can explore with this with. Okay, and so if you take a look at how WebGL came about, I think I put in some timelines here. It started in 2006 from Mozilla. It's an experiment. It came out. It went through standardization in 2011. Obviously, where we are with this, there's a lot of adoption talks that's happening right now. Browsers are adopting it, and there are a lot of popular apps. There's multiple frameworks that already support WebGL. So WebGL took a while, but I think people have started embracing this for their gaming, and that's giving you the render side of the performance. Now, what we're saying is on the compute side, where we need much more use of the heterogeneous computing, WebCL can help. So use WebCL along with WebGL, and you're able to use more of your cores effectively. Okay, so that was a quick introduction, and so we'll go a lot more deep into WebCL, how it actually works, how you write a kernel with it, and and we'll have some examples and some demos, and Swaroop is there to walk you through it. Thanks.
All right, can you hear me? Yeah, okay. Thanks, Satish. So before diving into this, just want to get a sense of, how many of you have kind of worked with OpenCL or know about OpenCL already? Not many, okay. All right, so I'll just step through some of the basics of what OpenCL is all about and how it can really help in game development. So first of all, it's a programming model, and the syntax is kind of very similar to C. It's in fact based on C99. And it has this concept of what's known as kernels. So these are, you can think of them as the equivalent of shaders for your compute-intensive operations. So these are actual programs that you can schedule to be run in parallel. And OpenCL runtime supports runtime build and compilation of these kernels. So you supply this source in clear text, and the runtime has the capability to compile it and run it just in time. That doesn't mean you can't do pre-compilation. You can definitely do that. But the fact that it can do that at runtime is kind of helpful for web applications in general. So you could really transport your source in clear text or whatever format, and then get it built on the end device you're trying to run it on, right? And it comes with a lot of nice things in terms of what you can really do within the kernels. It has a very rich set of built-in functions. It's very similar to what you would see in libm, for example. And it supports accelerated math operations, fast math, you can enable that. So essentially, it's a pretty powerful, runtime to exploit the hardware richness that you kind of witness in most of the devices today, right? And in terms of the programming model, essentially you have a host. So in OpenCL terminology, a host is a program that is actually using OpenCL. So you have some kind of a program like written in C, C++, Java, or a web application that is controlling how OpenCL is operating. So that is traditionally being referred as the host. And you have an OpenCL device, which are essentially a collection of computing units. So you could roughly equate them to cores on your processor or cores on the GPU. And then they are comprised of what are known as processing elements, or they're roughly equal to threads. So this is where a single execution happens within at runtime. And then the code can operate in both SIMD and SPMD mode, and essentially, it gives you the ability to take maximum advantage of the hardware that you have. That's the idea there. And in terms of the programming model, as I mentioned earlier, you have this kernel, which is essentially a basic executable code, similar to a C function that you could achieve both data parallelism and task parallelism. OpenCL supports both. And you have a program which is a collection of kernels and other functions. So kernel is something like a main function in C, if you will. So it is something that you could invoke from the host program. And you could have other functions which could be some kind of routines that you could call multiple times, and all these things clubbed together will make a program just like any other native program, for example, or JavaScript itself, for example. And you have a command queue on which you kind of schedule what you want to execute, and the queue execution can be performed in order or out of order based on what you want to achieve. There are various considerations there. And once you have all these things put together, you have a single execution. So let's say you have a 8-core machine, and then theoretically at least you could execute 8 instances of this particular kernel concurrently. So that's the whole idea, right? You're executing them in parallel. So each of those executions you can equate to a work item. So that's it's something like a thread executing your program, in the traditional sense. And then a work group is a collection of these work items, and essentially it's something like all the threads that are running on the same core, for example. So that's the logical view of things. Just to make it a bit more clear, if you take the example of image processing, you could think of an image being divided into multiple, image is actually built up of multiple pixels, let's say. And based on what you're trying to do, the granularity at which you want to achieve things could be, you want to work on individual pixels at a time. So when you map this onto an OpenCL kernel or an OpenCL philosophy, each of these pixels can become a work item within your kernel execution run. And the tiles within, it's basically a collection of these pixels or neighboring pixels can become a work group. And the idea is that you could take this piece of the image and then schedule it to work on a single core, and whatever is the algorithm that you're running, you could take advantage of the parallelism that exists in the hardware. In terms of the memory model that's supported in OpenCL, it's a hierarchical model, just like what happens in the CPU. It has a private memory, so each work item has a very small amount of private memory where it can store whatever is required, register values, etc. And then you have a local memory that is local to a work group. So this is shared among all the work items within that core. So they can use this local memory model to share results, for example. And then at the next level, you have this global or constant memory. So this is a piece of memory that's resident on the actual hardware that you're looking at. So it could be GPU memory or CPU memory based on what you're targeting. And then obviously you have memory on the host side also. So the memory management model itself is kind of explicit in that you as a programmer is responsible for managing how you want to move memory back and forth. So the responsibility kind of lies on the user here. Okay, so let's look at one of the very simple kernels, right? So the idea here is you kind of map your problem into what are known as n-dimensional computing domains. So for example, one easy way to kind of look at this is if you have an image, it's a 2D data structure. So you have height and width. And then if you're performing any operations on individual elements like pixels, so you would want to typically work in the 2D space. So in that case, it's a 2D computational domain. And similarly, if you are working on a mesh, the very simple way of looking at things is it's a 3D model. So you have X, Y, Z dimensions there. So then it becomes a 3D computation domain, right? And then the idea is that you can execute the kernel, which is the piece of logic that you want to use to compute something, to operate on a single point within this computational domain. So if you have a 2D grid, you want this logic to work on each element in that grid. And similarly, if you have a 3D mesh, you would want your logic to work on individual elements of the mesh itself. So that's how it maps into the computation or the n-dimensionality of programming or kernel programming there. So if you look at a very simple example, on the left we have a traditional loop that you can write in any language. This is shown in C, but this in JavaScript, this is what you do all day long, right? So you loop through your, so this, by the way, is doing vector multiplication, multiplying two arrays, for example. So traditionally, you would just loop through your array, multiply it and store it back, right? But in data parallel OpenCL, all you have to do is, the syntax looks very, very similar, and even the logically they're very identical. It's just that you have to take care of managing where the memory is or what type of memory you're using And then there are a few things that are kind of peculiar or unique to OpenCL. And so as an example here, when you do this particular call called get global ID, you're really getting the ID or the index into the work item. So within this global set of data that I have, what is my ID? And then you could use that to kind of retrieve data from this big chunk of data that was sent to OpenCL in the first place. So in this example, based on the ID, you're just fetching the corresponding data and then writing it back to the destination. And the nice thing is, if you have multi-cores, 8 cores, 8 of these operations are happening in parallel. So the speed up that you would see are actually very significant in terms of the raw computing advantage there, right? So in terms of executing the program, you kind of go through a number of things from the programming perspective. You look at what kind of devices that you have. So as mentioned earlier, OpenCL is supported on multiple types of devices. Your CPUs are supported, GPUs are supported. There is work going on to support other types of parallel hardware. But today, most of the usage is around CPUs and GPUs. So you as a programmer you have the ability to choose what you want to use for this particular use case, for example. So you query all the devices that are supported, you choose one of the devices, and you create a program, which is essentially a collection of code that you already have written. And then you create these programs for execution, and then you identify where you want the entry point to be, so which is essentially the kernel that you want to invoke at this particular point. And you manage the memory, or you create the memory objects that you want to pass along. So we'll see it a bit later, but in JavaScript terms, you could think of this as having a bunch of typed arrays that you're storing data in, and now you're pointing or kind of pushing that to the OpenCL layer for computation in parallel. So that's what you're doing when you're copying data into the device, or copying it down the pipeline, if you will. And then you schedule these programs that you have identified on the command queue for execution. Execute or issue an execute instruction to the command queue, and then you read results back. So this is the typical cycle in using OpenCL, right? So when we come to WebCL, the usage model is very, very identical. So even here, you kind of do the initialization where you're kind of setting up your devices. You select what you want to use, GPU or CPU, or if any other hardware is available, you would want to use that, etc. You create a kernel, which means that you have the source code, you build that source code, create an object in OpenCL, and then you run the kernel, which means that you're passing all the data that is needed for executing this particular piece of code, and then you're executing the code itself, which is scheduling its run on the hardware. So in terms of what it can do out of the box is, obviously the raw data types in terms of typed arrays, if you're creating yourself, you can obviously pass them along. But you have support for creating image objects. So if you're working on image processing, this is very, very handy. And then you could create image objects based on typed arrays, or if you already have an image that you've put on this on the web page, either through an image tag or a canvas, or it could be a frame within your video tag, you could grab that and process that using OpenCL. And also WebGL vertex buffers and WebGL textures. So OpenCL has this capability to play nice with OpenGL, which means that you could grab a buffer from OpenGL, do some processing on it, and then send it back to OpenGL for rendering. So essentially, this is the compute, high-performance compute counterpart for OpenGL. That's an easy way to look at this, right? So in terms of actual code, how would you, so this is WebCL again, how would you go about using WebCL, right? So the first thing to do is you look at all the platforms that you have. So when we, what do I mean by platforms is essentially you might have, you know, a set of CPUs and you have probably one or more GPUs that come with the device. So when you do this get platforms, it essentially returns you a list of all the supported platforms, GPU, CPU, etc., etc. And then you choose what you want to do. So for example, you can say get devices of a particular type from within the list of platforms that you have, and you create what is known as a context. So this is essentially handled into the OpenCL runtime or the device that you've chosen, and this is what you really use to kind of go forward or execute things based on, right? And as I mentioned earlier, you have this notion of queues. So this is a command queue where you schedule the commands that you want to run, and you get that. And in terms of the actual kernel code, the syntax is again very, very similar to C, as I mentioned earlier, and you could embed them in your web page, very similar to what you would do with a WebGL shader, for example. So you just have a script tag, and you just put the source code there. By the way, this is not the only way to bring OpenCL code into the program. You could easily have XML HTTP requests that will bring it in. You could read it out of a file, for example, or any other mechanism that would let you bring in strings, for example. And then in terms of the string, you're just, it's like reading source of script element within your DOM. So you pull that, use that to create the program. So you're passing in this particular statement where you're doing context.create program, you're essentially asking the OpenCL runtime to take the string and convert it into an OpenCL program. And when you build it, this OpenCL program gets an equivalent binary object created. That's what program.build is doing. And as mentioned earlier, your program might have a collection of kernels or collection of entry points that you put together, and you need to get a handle to one of those. So you might have a square operation happening. You might have, I don't know, matrix multiplication might be another kernel that you've written, and you have this library of kernels that you're going to use throughout your application. But by passing the particular name that you have, so whatever you have after kernel __ square, so that's what identifies the kernel name, and you pass that here to grab a handle to that particular kernel. Next step is to run these kernels, right? So in this step, so you have to kind of build the data that you want to pass and push it down the pipeline and execute the kernel. So that's what you're kind of doing from a higher level. So in our case, we are creating a typed array, populating it with a bunch of data, and then you enqueue these buffers, or data structures onto your OpenCL or WebCL queue. And there is a distinction between write buffer and read buffer. So write buffers are things that you can, when you say enqueue write buffer, you're writing into the memory or writing into your OpenCL system, and at the bottom you're doing a read back. So that's what enqueue read buffer is doing. And once you have the data set, you also want to set the arguments that you want to, or these are the formal parameters that you would pass to your kernels. So those are the, you set the kernel arguments, and the next step is to define the workgroup size. So the idea here is, you might have a particular data structure that you're working with, and based on what you're doing, you're dividing it into multiple dimensions, right? So if it's an image, you might work with a 2D kernel or a two-dimensional algorithm. If it's a mesh, you might be working on a 3-dimensional algorithm. So the idea here is, you can really define the granularity that you want to work with using this workgroup sizes. But for simplicity, here we are kind of letting the system choose what it wants to do in terms of dividing the work up. And that's possible if you just have one-dimensional data, or even for two-dimensional data. It's just that it's not completely optimized, that's all. And then you enqueue the kernel, or you schedule the kernel for execution, and you basically, the queue.finish that you see here is a blocking call to kind of flush your queue or execute everything that you've scheduled for execution on your queue so far. And then, once everything is executed, it comes back, you're ready to read the results back into your program. And that's what you're doing at the end there, right? So another simple example, it's essentially you're creating WebCL image object. So you already have an image from some source, image tag, canvas element, or video, whatever it might be. All you need to do is to say, you get the, you create the image based on, let me see here, hold on a second. Yeah, you just create an image object in OpenCL based on the data that you have. So this might be the data that you, for example, read from your canvas, and then you have the corresponding image object on the OpenCL side. So in OpenCL, there is kind of native support for working with images. It has a nice set of API or functionality that you can take advantage of in terms of achieving good speed up, right? So essentially, you could point to a canvas element, for example, like we're doing here, and then you could read the data in and work on that. Another example in terms of vertex animation, if you want to work on the vertices of a mesh, for example. Again, the philosophy is fairly similar. You're kind of creating these buffers where you want to populate the data and then pushing them down. But instead of kind of creating this data on the JavaScript side, now we are grabbing it from the GL buffer that you already have, because you kind of have a rendering representation on the WebGL side, for example. And what it's showing here is you could grab data from WebGL and then process it using WebCL, and then send it back to the GL counterpart for rendering. So this is going to give you a lot of speed up in terms of if you're doing complex operations, right? Similarly, you could achieve the same thing on textures. So you could create a WebCL buffer from an existing WebGL texture, and you could pretty much do whatever you want in terms of computing on the texture on the CL side or the compute side, and you could push them back to GL for rendering. Okay, so that's kind of the overall introduction to how you would work with WebCL. And in terms of availability, we kind of we have a way of this working on the Tizen device. It works in this, currently in this hybrid mode where you build WebCL as a plugin, and you could use it for Tizen applications. In the very near future, we're going to have native support for WebCL in the browser itself on Tizen. Apart from that, we do have a working implementation on the PC, works on Mac Safari and a Linux EFL port of WebKit, and it's available at that URL. It's very straightforward to build and use. Just make it and run the browser, and you'll have it working. You're welcome to contribute also if anybody is interested in working it out. All right, so let's look at some of the demos. So I'll show some of the demos on the screen also, but before that, I can just give you a quick video of what is happening here. So this is a simple application where it's calculating some deformation on the objects that you see within a skybox and rendering it within a skybox. So those spheres that you see, they're being deformed using some math background in the background, basically. So as you can see in JavaScript, it's not even 1 frame per second, by the way. It's taking way too long, but we're just capping it at 1. And in WebCL, as you can see, it's giving you significant speed up. So if you saw the times, it's 1400 versus 40 milliseconds. And you could even go down, as we see in the next demonstration. It's, you can kind of work within the time budgets that you have. So, either 16 milliseconds for 60 FPS or 32 milliseconds for 30 FPS. You could work, do some nice things within that time budget in terms of computing that you can do. So we're putting together a gallery also. It's not there yet. It's coming together. This will be a nice place to kind of work off of existing code, and you could kind of take that and make it your own by modifying a few things probably. This is something that's coming. And I'll just leave it at that. We always look for collaborators, and you're all welcome to work with us. And let's go to the demos, if they work. All right, so this is our Tizen prototype. So the first demonstration I'm going to do is basically the video that you saw there, just to show that it's not a mock-up, it's something really working. So, without any simulation or without any effect. So essentially, you could think of this as a special effect that you would want to apply to your game, for example. So without anything, it's running at 60 frames per second. I'm going to switch it to JavaScript mode. It's going to take a while. It's going to drop in terms of the performance. It's giving you 3 milliseconds right now, for example. So this is a mesh of a lower resolution. The one that you saw in the video is a higher resolution mesh, but it's going to fall down even further. Now when we switch it to the WebCL mode, you're getting a significant speed up again, something like, I don't know, so many x, 30x or 25x in this case. So by the way, the speed ups that you get are not constant. They vary based on what you're really doing within the kernels. But in this particular use case, you're getting fairly significant speed up, right? So next application we want to show is, let's see, rock and roll. Maybe I can put it this way, right? Okay. So this is, again, I'm not going to go through the complete game. I'm just going to show, the speed up part of it. There is a game also that's working. So here, the background, if you see the animation that you see in the background where it's kind of shaky, that's what we're using WebCL for. So we're taking the texture from the game itself, and we're kind of moving things around a bit to make it a bit dynamic. And if by the way, the current frame rate is somewhere between 45 and 55 or so. And when we switch it to JavaScript, you see that it kind of drops significantly, right? So this is 45 to 55 is acceptable for games, especially web-based games, I would assume. But if you're getting like 6, 7 frames per second with JavaScript, this is something that you really, really need to worry about. And in most cases, you would not use something like this, right? So, this is another example. Let's see, the next one. Where is toxicity? Here, okay. So this is another simple example. It's again the sphere deformation that you saw. We've just put that into game concept here. The idea is that you have these objects that have been released, and you need to pop as many of them as you can to kind of save your city. So that's the idea. But right now, as you can see on the top right corner, the simulation is off. Let me switch to WebCL mode. The frames per second that we're getting is around 40 frames. I'm not sure if you can see, but at the bottom left corner. And switch to JavaScript. So by the way, the effect is very similar to what you saw in the spheres, right? So in JavaScript, we're getting 5, 6 frames per second. So that's the kind of acceleration or difference in performance that you can expect with WebCL. And it's not, again, it's not just limited to textures or meshes. It's raw compute, right? So you could use it for other algorithms. For example, if you have I don't know, you want to do collision detection for a particle system, for example. This could be handy there. We're working on some effects for soft bodies. It wasn't ready for in time here, so we're not showing. But there again, you have a lot of compute that you really have to do apart from what you're doing on the render side. And we think WebCL is essentially the answer to such challenges. So with that, I'll be happy to take any questions you might have.
So if you've got question, I've got the mic.
Hello. We saw on the previous presentation that WebGL was available mostly on every browser. So what about WebCL? So you said it was working on Tizen. What about Firefox, Chrome, or?
So it's a standard that's being worked on right now. So unlike WebGL, which is kind of adopted widely, WebCL is in the standardization process. So we've seen quite a bit of enthusiasm and interest from various vendors, and we hope that it's going to be widely available, at least as wide as WebGL in the very near future.
Hi. If you want to do a real-time computation, do you have to repeat every step with setting up the kernel?
No. So this is like initialization, right? So you do that once, and once you have it, you could execute or kind of invoke the kernel. So it's just the execution part that you might have to repeat all over again, which is q.finish, for example. But if you have to retransfer data, that's also something that you'll have to do. So, for example, if you want to bring back the process results into JavaScript for any reason, That's another step that you would have to do every execution. But otherwise, you do it once and you're set. And by the way, this is the raw APIs that we're showing, right? On top of this, you could, we have initial versions of those also. You could have a nice abstraction, just like what 3JS and Babylon does for, games, for example, and give you that API that is easier to work with also. So that's something that will really help also, yeah.
So you just answered the question I was about to ask.
Okay.
But do you know of any abstraction layer, framework above WebCL about to appear? Because the whole thing, the low layer is going to be a bit complex for too many people, I think. It's extremely powerful, but you have so many things to masterize, it's going to be complicated. Is there any framework in the pipe or anything?
Yes, but
Yeah, we're working with a few game framework companies, and it's work in progress. Nothing there that we can declare at this point, but when it's ready, yeah, we'll definitely make. So that's one of the efforts that we want to do, where one of the paths to make it widely available is integrating with game engines and making it available through that. So.
Any more question before the break? Yep.
Actually, I wanted to ask about Tizen. Will it be released only on Samsung phones, or will it be available also on every other phones? Like
I don't know. I'm not really sure on the the product cycle of things. I'm a part of a research lab here, so I know as much as you do, basically.
Okay, so you don't know what is the level of advancement of the project?
Of
how much is Tizen ready for the public and so on?
I mean, it's an open source project, right? So everything is in the open now. So you could go to tizen.org, build your own image, put it on a piece of hardware and test it. But in terms of the products, that is something that I don't know. I kind of am familiar with the technical side of things.
Okay.
I guess all these are not exactly technical, so I can't answer that. I'm sorry.
It's okay. Thank you.
Hello, I'm using Tizen right now, and on the 2.2 version, we had a lot of person had a problem with dump panic error. Do you have a fix for this problem?
I'm sorry, can you repeat that? I can't.
I'm using Tizen right now, and a lot of person and me have a problem with in the starting when I turn on the device. There is a dump panic error, and the device not on.
I don't know. So is your image corrupted or something like that? It could be that. I'm not sure.
I don't know. I'm just turning on the phone and error, and then it shut down.
Yeah. So probably I don't know. There could be multiple reasons. Your bootloader is corrupted, or the image is bad.
Okay.
Yeah. I'm not sure. Sorry.
So maybe you've got specific question to WebCL rather than Tizen. No? So, yes? Jean-Marc? We're talking in English here.
Hi, I wasn't here for your presentation, so maybe I'll ask a question that you already answered. I'm very sorry.
No problem.
Today we have OpenGL to WebGL bindings using Mscript 10. Can we expect the same kind of bindings for WebCL and OpenCL? So, for example, the build physics engine could be hardware accelerated inside Firefox, for example.
That's a very good point. Yeah, I mean, it's something that definitely can be done. We have not done it yet, but we are open to the possibility there. Yes. it's an excellent way of utilizing what's out there. Sure, yeah.
So well, then I'd like to thank you.
Thank you.